So, we have been talking about RAM test generation algorithms, like how to for generating the test patterns for RAM, what should be the technique. And this test generation algorithm, essentially it comes with the set of the read write sequences. In fact, for testing a memory, ultimately we need to write some bit pattern there and check whether the bit pattern has been correctly written there or not by doing a read operation. And similarly, if we want to modify one location, so it should not be the case that some other location also gets modified due to that writing. So, basically we need to do some read write operation over the memory cells to check whether the memory cells are working properly or not. So, when we talk about RAM test algorithm, so that is basically talking about a sequence of test elements or sequence of patterns to be applied for testing the particular memory. So, a test algorithm or simply test is a finite sequence of test elements, where each element has got a number of memory operations. So, memory operations are read and write operations. So, basically, so it may be operation like a read followed by so it may be the operation like write followed by a read. So, if we write a 0 and then we would expect that while we are reading we will get a 0. So, write 0 followed by read 0 may be testing a cell for possible fault of stuck at 1. So, like that we can have a set of these patterns to be written. So, this so it contains a number of operations. So, that is what it is called access commands or operations to memory operations to be done. So, while doing this, so this memory command, so they will create some background pattern on for the memory. So, while we are writing some pattern, so it will create some data pattern through this write and read operations that will take place. So, that is one part, and the second thing is that we have written say at cell number 10, then where are we going to do the next memory operation? Is it at cell number 9 or at cell number 11? That is whether we are going to apply the next read write command on the next memory cell or the previous memory cell. So, we are traversing the memory in an increasing address order or a decreasing address order. So, that actually the address sequence specified for the read write operation. So, when we are talking about a test element, we are talking about these two things, what are the commands to be executed and the sequence of addresses of the cells in which these commands are to be executed. So, the most popular memory test algorithms, so they are known as march test algorithms, because they talk about some marching pattern through the memory cells. So, it write some pattern and try and read it. So, it is a marching pattern. So, it has got a finite sequence of march elements. So, some march elements are applied, and that way we test the faults that may have cropped up into the memory array. So, a march element is naturally specified by an address order and a finite number of read write operations. So, march test notations that we will be using, so these are very standard notations, like say this up arrow coming before the march element. So, it will identify that the operation specified in the element should be applied to the memory cells in an ascending order. So, address will be in ascending order. First it will be say writing at cell 0, then cell 1, cell 2, that way the address will be in ascending order. Or it may be the down symbol. So, that is the address changes in the descending order. So, while we are applying the patterns to the memory array, so for testing it, so address should start with the highest possible address, and then the address should go down after the read write operations at individual cells. And the third one is either way. So, this here actually this means that the element can be applied in any order. It does not matter whether it goes in the upward memory address increasing order or in decreasing order, that does not matter. So, test coverage and everything will remain unaltered. And as far as the operations are concerned, so as we know that memory, the operations are a read operation. So, it may be when we will represent it by R, and or it may be a write operation. So, we will represent it by W. So, while we are writing, so we can write a 0 to the cell or we can write a 1 to the cell. So, this W0 or W1. Similarly, when we are reading from the memory cell, so we expect that we may expect to read a 0 or we may expect to read a 1, For example, if the just previous command was a has written a 0 to the cell, then the next command should be trying to read the value from the cell and the expected value is 0. So, if you get the value read from the cell as 1, so you understand that okay, there is some problem with the cell, so there may be some stuck at fault. So, that way we can identify the faulty situation. So, this reading is the expected, the value that we expect to read is written after this after R, and similarly the value that we are going to write to the cell is written after the letter W. Okay. So, for example, this is maths plus is a march test pattern. So, here it says so this has got 3 march elements, or this is the first one, this is the second one, and this is the third one. It says that the first one can be applied in any order. So, either increasing or decreasing order, and it will fill up the entire memory with 0, because it says that write 0. So, all the cells they will contain now 0. The next, so the first template will be for the entire all the cells, this first template will be applied. So, all the cells are now containing 0. Then it will come to the next template. So, here it says that you do it in the ascending order. First you read the content of the cell and expect the value read to be 0. Naturally, we have written a 0, so we will expect to read a 0, and if it is not correct, then there we can detect the errors, that the stuck at 1 type of error, and then we change the pattern to 1 for that cell. So, we have read a 0 and then we are trying to write a 1, and similarly when this template is over, that means for all the cells they are now having the value 1. So, next we do it in the decreasing memory order, starting with the highest memory address. So, since we had written a 1 at the last place, so we expect to read a 1. So, we read a 1 and then we write a 0. So, that again fills up the location with 0. So, this is one particular march testing sequence. So, this has got 3 march elements in it. Okay. So, this will detect different types of errors, like it can detect some sort of coupling between the cells also, like you see that say suppose there is a coupling between 2 cells. So, for the first cell which came earlier, so there while we are doing this write operation, the second cell also got modified. So, it was 0, but it became 1. So, when this R0 will be done on the second cell, there will be a failure, because it will the system will find that the cell is now containing 1. So, that type of coupling can also be detected. So, this way you can analyze what are the faults that can be detected if we follow this type of read write pattern. There are many such march algorithms. The first one is known as the M-scan algorithm, or memory scan type of algorithm, as because it scans the memory from one end to the other end. Okay. So, this is also known as the 0-1 algorithm, and proposed long back. So, it is 1976 it has been proposed, so long back. So, stuck at fault is detected if the address decoder is correct. So, this is the property. So, it can be shown that if your address decoder is correct, then all the stuck at faults can be detected. So, you see that this ultimately the pattern is like this. So, you in the increasing order you write 0, then in the increasing order you expect to read a 0 value, then in the increasing order you write a 1, and in the increasing order you try to read a 1. So, you see that if there is no address decoder fault, then this part will detect a stuck at 1 fault, and this part will detect stuck at 0 fault, because it is expected to we have written 1 and expect 1. So, if that is remaining 0, that means stuck at 0 fault, similarly this one. So, if the address decoder is has some problem, then of course some other location may get selected. So, you cannot be sure whether it is a fault, the stuck at fault, or it is an address decoder fault, but assuming that address decoder is okay, so we can detect all the stuck at faults. So, there is a theorem that says that a test will detect the address faults if it contains the march elements in this way, the increasing order RA and write A dash. So, A and A dash, so they are actually complementary to each other. So, if A is 0 and A dash is then A dash will be 1. So, like that, or and vice versa, if A is 1, A dash will be 0. So, that is vice versa. So, if your set of march elements contain these 2 march elements, that one march element starting with RA ending with write A dash, read A and write A dash, and another march element coming in the descending order starting with read A dash and ending with write A. So, this will be able to detect all address decoder faults. So, this particular so that actually tells that all address decoder faults are not covered by this particular this M scan or 0 1 algorithm. So, it is a solid background pattern, because the background is at any point of time, if one template is over. So, the memory background is having all zeros or all ones. So, that is why it is called a solid background pattern, and complexity is 4 into n. So, n is the number of cells that we have in the memory. So, there are so how many such read write operation, or how many memory accesses we are doing. So, that determines the complexity of this merge algorithm. So, you see that there are 4 such operations to be done on every cell. So, that is why the total complexity is 4 into n. Another algorithm which is known as checkerboard algorithm. So, checkerboard algorithm, so this is again a 0 1 algorithm with checkerboard pattern. So, checkerboard pattern means the at any point of time when you have completed one particular template of this merge sequence, the pattern in the memory should be like this. So, alternate locations will have ones and zeros. So, again this is complexity is 4 into n. And so, this point is important. It says that the must create true physical checkerboard, not logical checkerboard. So, what it essentially means is that, see, we are, if we have got say a memory of say 1024 locations. So, 1024 you can, if you are breaking in a 2D form, so you can break it in different ways. Now, while we are doing it, so it is not mandatory that a particular cell I and the cell I plus 1, which are logically close to each other, will also be physically close to each other. So, they may be far away in the actual layout. So, what it says is that in the actual layout, this checkerboard has to be created. So, it is not a logical checkerboard, but a physical checkerboard that we have to do. So, this type of checkerboard algorithms, so they are good for stacked fault and data retention fault. So, data retention fault means we write some value there, and it is expected that the value will be retained, and after some time we again do a read operation. So, we find that the value has been changed. So, it is normally detected by 2 or 3 successive read operations. So, that way if the data is leaking, if the cell is leaking, then the data will get lost. So, that is the data retention fault. Then we have got shorts between the cells and half of the transition fault. So, they will be covered, but not good for address faults, and not good, and some of the coupling faults are also not detected by this checkerboard type of algorithm. Complexity is 4 into n. Another very good algorithm for this testing, memory testing, is known as GALPAT or galloping pattern algorithm. So, this diagram actually tells what it essentially tries to do. So, it says that, okay, I have got say total n number of cells. So, out of that, this BC is the cell that we are considering now. So, what we do, we first write background to be all 0. So, first entire array is filled with 0, then we take any of the cells. Suppose we have taken up say this particular cell. So, we complement this cell value to 1. Okay. Then we read the, now we take up, or now we consider all the cells, all other cells in the array. So, we take up this cell, we read the content of BC, and then again read the content of the cell, the OC cell. OC are basically other cells. So, OC you can read it as other cells, and the BC is the cell that we are considering now. So, what we have done, we have complemented the value of BC, then we read the value of then we have read the value of BC here, and then again read the value of OC here. Then again I am reading the value of BC here, I am reading the value of this particular cell, then again reading value of BC, and again reading value of this cell. So, this way actually it after finishing or reading all the bits in this all these bits, again we complement the BC and again repeat the whole process. Okay. So, again it is for the next cell it will be done. So, you see after complementing BC, so that is for only for one cell, then again we try with the next cell. So, this way it is for every cell we are checking, we are reading all the other cell contents. Okay. So, that way the algorithm is very costly. Okay. And then that is with a background 0, and after that we make all entire background 1 and again do the same thing. So, this way it can cover most of the faults. So, it is a very strong test, and it covers all address decoder fault, all transition faults, all coupling faults and stacked faults. So, stacked faults, in fact, you can locate specifically where exactly the stacked fault has occurred. So, complex, so that way it is a very strong testing. Okay, so, it can detect large number of faults, different types of faults, but the complexity is very high. So, it is 4 n square. So, in some lecture we have seen that since the value of n is very large, so some algorithm which is more than linear time consuming one, so that is considered to be very costly. So, if we, so 4 n square is a really costly algorithm. So, it is, that is why it is said that it is only used for characterization. So, if you have to do some sort of benchmarking of some memory test algorithm, so you can compare it with GALPAT. For some small memory, you can try doing GALPAT and your proposed algorithm, and try to see which are, how close you are in detecting the faults that are detected by GALPAT as well. So, that is why it is used, it is only used for characterization. Another variant of this GALPAT is known as the WALPAT algorithm or walking pattern algorithm. So, what it says, it is similar to GALPAT, but except that the BC, the base cell that we are considering, that is read only after all others are read. So, we complement this, that is fine, but then we read all these cells. So, in case of GALPAT, what was happening is that after reading every cell, so you are again reading the base cell. So, that was repeated every time. But now it is not that in WALPAT. So, we once we are reading this cell, so we read all these cells, okay, all these cells which are excluding BC, and then again we read BC and again they repeat the process, complement the BC and again read the repeat the process. So, that way this WALPAT algorithm complexity is less compared to GALPAT. So, it is 2 n square, but still it is in the n square domain. So, that is why it is still a very costly algorithm. Now, simple tests, so like the 0 1 that we have already discussed, the M-scan algorithm. So, there are some modified arithmetic test sequence or MATs, so in short form it is called MATs. So, it can detect address decoder faults. How? So, say this one, say this can detect odd type address decoder fault. So, odd type address decoder fault means for technologies where the result is OR type. So, what we mean is that suppose one address, it selects two different cells. So, this cell as well as this cell due to the problem with the address decoder. So, these are the memory cells and this is the address. So, both the cells are selected. Now, what will be the output, because ultimately RAM output is coming via that sense amplifier and all those things. So, in odd type technology, it says that the result is basically an OR of these two. The result that you get is OR of these two. So, for this type of technology, so this particular the sequence that is shown here in this MAT sequence. So, this first you write, first you initialize the entire array, entire memory with zeros, write 0, then we then again we start, then we check individual memory locations for a read a value 0, and then we write a 1, and then after that we expect that we will, when we read, we will get a 1. Now, you see in OR type of situation, what will happen when say this cell was accessed, when this cell was accessed in the second when this cell was accessed in the second template, that is R0W1. So, when this, while I was doing a write operation here, maybe this so this cell also got modified. So, this cell also became 1. So, as a result, this R0W1, this particular template, when this R0 is done on this cell, so it will fail because it is already 1. So, for odd type of technology, so this will be determine this will for odd type of technology. So, this will be detecting the fault, the address decoder fault. Similarly, AND type of technology means the content of two cells getting selected, the contents will be ANDed to know what is the final output. So, for that type of situation, so this particular sequence will be doing the thing. So, it is R1, so first we write all 1, then read 1 and write 0. So, and it will modify the second cell also to 0 when we do write 0 on the first cell. So, it will also modify the other selected cell as well. So, that will also become 0. So, this read 1 will fail in that case. So, we see that for odd type and AND type this MATS algorithm, so it can detect the address faults. Now, a modification of this MATS is MATS plus. So, it says that it will so it will be determining both OR and AND type faults. So, you see that this one R0 W1. So, this is this will be determining OR type of faults, and this R1 W0 will determining the AND type of fault. So, both are detected by the MATS plus sequence. Then we look into marching 1-0 pattern. So, this is another march test, marching 1-0. So, marching 1, it begins by writing a background of zeros and then read and write back complement values and read again to verify. So, for all the cells. So, this is basically this one. So, first it will write write background of 0. So, this first write W0. So, this will do that. Then it will say read and write back complement values. So, I am reading the value, writing the complement value, and then we are again reading it to verify. So, and read again to verify. So, this read 1 is again to verify. Okay. So, this will be this is done here. So, this is for 0, and then I have to do it for 1. So, again I am doing a read 1, write 0 and read 0. So, this is one sequence. So, marching this is marching 1. Similarly, I can have a marching 0. So, this will have a marching 0 sort of thing. So, here this particular sequence, so it can detect address decoder fault, stacked fault and transition faults, but only a part of the coupling faults. It is a complete test. So, this is important. It says that all faults that should be detected are covered. So, all the detectable faults, all address decoder faults, stacked fault and transition faults, they are covered by this one. However, it is a redundant test because only the first 3 march elements are necessary. The rest part, though it is telling marching 0, but that is not necessary. So, first part is sufficient for doing this. So, this redundancy proofs and all that we are skipping. So, it is there. So, if you refer to the corresponding paper, so you can find it. Then we have got MATS plus plus. So, MATS plus plus, it is good for addressing address decoder fault, stacked fault, transition fault and all that. Optimized marching of 1-0 sequence, it is complete and irredundant. So, this is the MATS plus plus sequence. So, first it writes 0, then it reads 0 and writes 1, then reads 1, writes 0 and reads 0. So, again it can detect all the stacked faults and transition faults. Then we have got March X algorithm and March C algorithm. So, these are the 2 other March algorithms. Actually, what happened is from the inception of these memories, when the designer started doing this manufacturing the memory testing is always there. So, before this March algorithms came into market, so this the researchers came up with this proper concept of March elements or March test. Memory testing was being done. So, some of the March tests, so they were used even before they are actually available in the literature. So, before being published, so March X is a sequence, is a testing sequence that is useful, that was used before this before it was reported in the literature. So, this one, so it can detect address decoder fault, stacked fault, transition fault and coupling fault. So, all of them can be detected, and then we can do it in a. So, this is the sequence. So, first it writes 0 to the background, then it does read 0, write 1, then it does read 1, write 0, and then it again reads whether the 0 has been written properly or not. So, that is done. So, this can detect all these types of faults: address fault, stacked fault, transition fault and coupling fault. Then there is a March C algorithm. So, March C algorithm, so it the sequence is proposed is like this: first write 0, then read 0, write 1, then read 1, write 0, then read 0, write 1, etc. So, this is again good for address fault, stacked fault, transition fault, coupling faults, but it is semi optimal because some of these operations can be removed. So, there is there is a redundancy. So, some of the operations can be removed. So, if from the march C, if we remove this redundancy part, then what we get is the march C minus. So, in march C we have got this sequence, in march C minus some of these redundant parts are removed. So, this is the march C minus proposal. Okay. Actually, all these are test algorithms. So, different people at different points of time have come up with this test algorithms. So, that is why we are reporting all of them. So, march C minus is reported to be doing like this. So, write 0, then read 0, write 1, then read 1, write 0, read 0, write 1. So, like that it is done. And then an extension of march C minus, it covers this stack open faults in addition to these faults like this address fault, stacked fault and all that. So, stack open fault is also covered. So, this is the sequence for that. So, you can to get a confidence that it really determines these errors. So, we have to take individual errors and go through these individual sequences to locate where exactly which particular pattern is going to catch it. So, here we are just taking it as accepted that they are doing these faults are getting detected. So, the actual analysis you can find in the corresponding literature.